Also know from linear algebra that the sum of the eigenvalues for a matrix is equal to its trace. Did you ever see Did you ever see that? Well, I can. Let me show you why that's true. If we calculate the trace of A, and A is diagonalizable, I'm assuming that at the moment. So this is going to be the trace of P inverse AP, where P is the diagonalizing matrix. See, because the trace is cyclic, we can pad it with P and P inverse. It doesn't change the trace, right? But then this is the diagonal form of A, which we're denoting like this. And that is equal to therefore the trace of A is the sum of its eigenvalues. And my bad, I think I've missed something along the way. I lost my exponential of the trace, right? Duh. I had e to this, right? It's e to the, maybe that's what you're puzzling over. If so, good. I would argue every student of linear algebra should see these things in the course. Like, this should be standard. Your linear algebra course should show you this. No excuses. I'm sorry. I don't care what school you go to. You should see this. In the diagonalizable case. All right? Now, this is still true when the matrix is not diagonalizable. Because the same calculations go through for the Jordan form. And an arbitrary real matrix is, okay, fine. If you complexify the matrix, it has a complex Jordan form, and this calculation goes through for the complex Jordan form. Or if you like, you can form its real Jordan form, and this calculation goes through for the real Jordan form. All right. That's the other interesting kind of matrix group that I haven't talked about yet. Well, there are many, but all right. Let me not. I can chase these rabbits very far afield. So let's stop right there. The point is, there's a matrix exponential. The determinant of the exponential is the exponential of the trace. This is wonderful. Wonderful to know. It's going to be very helpful for us as we're studying the questions we're studying at the moment. I'm going to erase this right now. Is that okay? I think you already got it.
Oh, exactly. Okay.
Yeah, you were fine. You were fine. Okay, so what's going on here? Well, yeah. Skipping back to oh man. I gotta get some gum or something on these days. All right, so in a manifold, all right, one of the interesting things we study in a manifold is the tangent space. So like you've seen this in Calculus 3. We can talk about the tangent space to a surface, right? We spent some time calculating these things because you need to understand the tangent space to set up the flux integrals, things like this. But this concept generalizes to an arbitrary manifold. So a tangent space is what it sounds like. It's the space of all tangent vectors that go through a given point. So generically speaking, if your picture, here's like a picture, just a very sketchy picture of a Lie group G. There is a special point on a Lie group. Every Lie group has this point. Every matrix Lie group, which is a subgroup of GLN, has the n by n matrix as a point in the space, I. All right? And so it makes sense to look at what's called the tangent space to the identity. All right, so I can kind of picture it, roughly speaking. It's something like it's a flat, it's a tangent plane, and you can think about that as being filled with all of the possible tangent vectors that emanate from that point. Yeah, thank you, Audric. So this would, a notation for this would be the tangent space to the identity of G. Well, what I want to explain to you is that the tangent space to the identity of G is not a group. However, it does have a special structure. And so the usual notation for this is like, this is frac G. It's a fracture G. All right, so let me see if I can try to backtrack this more. So the Wikipedia article, it just comes down like a sledgehammer. It's just like you define it like this. It's like whoa, that's really man, I gotta find that definition. Where'd that thing go to? Oh man, I can't find. I need to learn. Print first, read second. Because if I read and don't remember where it is, it doesn't help us. Yarr. Oh, there he goes. There he goes. Here's his super greedy definition. Here he goes. Adjusting slightly, but here he goes. Lie G is equal to, and now he's got it for complex, but I'm going to do it for real. So X in, well, I guess my notation is usually not that. My notation is typically R n by n. So n by n real matrices such that exponential of Tx is an element of G for all T and R. So yeah, G is the matrix group, and I'm arguing that up to some reasonable identifications that this is equal to G. So here I'm making the identification, Audric, that since we're working with matrices, we can identify the tangent vector with its coordinates. Like, you know what I'm saying? Like, I'm not thinking of these as derivations, all right? I'm thinking of them as, literally a subset of matrices. Okay. This is possible because we're dealing, it's because of the context we're in. But, so, let's see here. Now he claims, Wikipedia claims that you can show that this is a vector space.
Well, I mean, from the construction, yeah, it makes perfect sense that a
tangent space to a point would be, can be considered a vector space?
Well, sure, but it's not at all clear to me that if you take the x's such that the exponential is in G like that, that's a, like, why is that a vector space?
No, yes.
I mean, totally agree with you, Audric. Like, this is almost by definition a vector space. I mean,
Yeah.
and so I'm not sure it's really different either. Let's see here. Let me try to process this more. So is it? I was thinking it's the inverse image under the exponential. It's not quite that though. Never mind. I thought this was more streamlined than it is. Let me put it into more concrete terms. All right. So V is an element of the tangent space to the identity of G if and only if V is equal to gamma prime of 0, where gamma is a mapping from, let's say, the reals to the group, such that gamma of 0 is the identity and gamma prime of 0 is V. So this, what I just wrote, is essentially the definition of tangent space. Like, the tangent space, it's the collection of vectors which appear as tangent vectors to curves. So like gamma is literally a curve, right? A path through the origin. So like, you know, I could picture it. See, like, maybe this is the curve, this is the path, right? This is the gamma path. And then this particular one is V. And you can use that to define frac G. I don't know if that's really different. See, because the thing is, you might say, well, that looks really different than what you have written right above, right? Like, there's no matrix exponential in all this, right? See that? There's no matrix exponential in what I've written here. Yeah? But check this out. Here's where the connection happens. Lemma. If gamma of t is equal to e to the, let's say, tx, then gamma of 0 is equal to I, and gamma prime of 0 is equal to, well, so what happens when you differentiate this? Remember, we proved before. We proved that we proved that we proved that the matrix exponential, when you differentiate it, it's x times the matrix exponential, right? We proved that before to show that it was a fundamental solution matrix to the system of differential equations. See, this is part of that story. So put times 0, what do you get?
Oh, just x.
Yeah. Right. So you see, whatever you're putting here that becomes what's in the Lie algebra. Now you can't just put anything here, mind you, because whatever you put here, it has to exponentiate to be in the group. So not just any matrix can go here. One whose exponential is in the Lie group.
And those are the paths.
So a string is attached. Now you say, well, that seems really, really, really complicated. How do I, but you define, I mean, you erased it all now, right? But you had defined groups in terms of these various conditions. How am I gonna filter those conditions through the exponential? Well, it's more simple than you think. It's actually pretty simple because, well, let's just try it. All right. And so actually the exponential map, I've been talking about the matrix exponential, but this is not special to matrix Lie groups. If you talk about Lie groups in the abstract, the exponential is defined essentially by like this definition, something like that. Like essentially you use the paths through the identity to define the exponential. You look at these things called the one parameter, like there's one parameter group of curve, one parameter subgroups. You take a course in Lie groups, you'll learn about all this stuff, okay? But my point to you is just that this exponential, being the matrix exponential, is just the tip of the iceberg. There's a more abstract notion of exponential on a Lie group, which is still defined. All of these calculations still go through. They're just not the matrix exponential. They're something more, a little bit more abstract. Okay, so check this out. What is then the Lie algebra of big G? So what if we look at, you know, what is Lie of big GLN? What do we need? We need, do you want me to use an X or a V? I'm going to use a V, if you don't mind. I'm going to shift over to V again. For V to be in there, we need that E to the TV, right, is an element of GLN. So what does it take? What does it take for E to the TV to be an element of GLN? This is a horrible example to start with. There's nothing to see here. It's automatically true, right? In fact, it's automatically true not just for invertible matrices. It's true for V being any matrix whatsoever. So this is a tautology. It's automatically true for any V, for all T. So this implies then that the Lie algebra of GLN, it's just equal to Rn by n. And we have notation. So you usually use this notation, little GLN R. Little GLN is the Lie algebra of big GLN R. So there's more, and I haven't quite explained this yet, but okay, so in the group, right? In the group there is multiplication, right? Matrix multiplication is the group operation. This algebra, like an algebra usually has some kind of multiplication. What's the multiplication for these Lie algebras? See, we haven't touched on that yet. What is that? You know, what is the operation, if you will, for the Lie algebras? I'm not sure off the top of my head if I'm able to derive it for you guys at the moment, like I'm afraid to try. I feel like I might just waste a half hour of your time. So I'm thinking, how do we understand what the structure is for the Lie algebra from the Lie group?
Well, are we defining it in the natural way? Like,
Okay, how would you define it in the natural way? What would that mean?
yes, you have a group, like all algebras have underlying group structure in them, through their fields, rings, ideals,
Uh-huh.
And so, for this Lie group to be extended into an algebra, we would need to add at minimum, a multiplicative, we need to add more operations on the group.
Yeah, let me think more. Let me think more about this as I talk to you about it. Maybe something will pop into my head, but at the moment, I don't know quite. It's not true though. Like there's no identity on the Lie algebra.
Yeah.
It's not like that. It's an.
So they're completely different notions in that?
Yeah. The Lie algebra is. It's not a group, except in the sense of it's a vector space, so it's a commutative group.
Yeah.
But it's not a group in the sort of more ring sense.
Yeah.
But okay, so
Does G have two operations?
does G have two operations? You mean frac G?
Yeah.
Well, it turns out that frac G is going to be closed under the commutator bracket. So just to, I wanted to motivate this, but it is true that if you take, let's say, a V and a W from G, all right, then the commutator of V and W is going to again be an element of this frac G. So sorry, this angle of thinking about things kind of snuck up on me. I don't know if I've thought about this before, or not recently anyway. I usually think the other way around. I think about if I'm given a Lie algebra, how can I define a Lie group? See, and from that direction, it's easier because if I've got e to the ta times, well, let's say v, e to the tv times e to the tw, well, that's e to the t times v plus w plus 1/2 the commutator of v and w plus 1/12 the commutator of v and w with v again minus 1/12 the commutator of v and w with w again. I think I'm a little bit sketchy on the signs here. But the point is, if you know the values of the commutators and the nested commutators, then that means you can define how to multiply two exponentials using the rules for the Lie algebra. See, if I know values of the bracket, then can multiply the exponentials. And I think I got it backwards. Look at this, guys. Man, I got it all twisted. It's the other way around, right? Exponential goes from the Lie algebra to the group. Goodness gracious. Oh, so sad. Sorry about that. Oh, goodness gracious. That's not a good sign. All right, so let's calculate the Lie algebra of something more interesting. How about SLN? Is this example 2? I guess this was example 1. Finally, we had an example today, right? So example 2, let's calculate the Lie algebra of SLN. So how's that go? So what we want to think about gamma of t, right, equal to e to the tv being an element of SLN for all time, right? That condition holding is what is needed for V to be in the Lie algebra. All right. So how's that go? You guys, well, you remember how we defined SLN? It was the determinant of e to the tv is equal to 1. But we had a formula. That's when now the formula is awesome. Because the formula said that this was really what? The exponential of the trace of tv, is that right? Determinant of the exponential is the exponential of the trace, right?
Yes.
So we don't care about t, right? This has to hold. This is an identity. It holds for lots of times. What's the time we'd like to think about? Zero is true. Hello? Oh no. When? Where? Do you need me to come home to take Isaac to practice then, or? Oh. Okay. Well, if you can drive and you think it's safe, it's okay, but yeah, we'll do that. No, I'll figure something out. Alrighty. Okay. Well, I'll try to be there like we planned. All right. Okay, it sounds like a plan. All right. Love it here. Right back. My idiot son was fooling around with his mom, and then, no, this is how I'm going to tell the story, is that he pushed her off the road. I think that's not accurate, but she like fell in like the ditch or something, and she's like turned her ankle or something, so it's not good. But so did you guys figure out what T should be?
No.
God, there's two choices. I already ruled out 0. 0, I mean, 0 is true, right? Okay, so the exponential of 0 is 1. Yay, we've learned nothing about V, right? We're interested in V. T equals 1. T equals 1. That's what you want to do. Put T equal to 1. There we go. How does this happen?
Well, we just add up the
Yeah. Well, that is how to calculate the trace. True. But what does this say? What is the trace of v equal to? Yes, the trace of v must be equal to 0. That's the condition. That condition suffices to make the image of the exponential, right, of t times v in the special linear group. So, and this is why we define SLNR is equal to, let's say, v in Rn by n, such that the trace of v is equal to 0. And this is the special linear algebra. The special linear algebra is the Lie algebra of the special linear group. The general linear algebra is the Lie algebra of the general linear group. Let's do a case study here while we're at it. I found a dimension by some figuring for SLN as a Lie group, right? As a matrix Lie group. Fundamental fact of manifold theory: the dimension of the tangent space is the dimension of the manifold. If you've got a two-dimensional tangent space, you're talking about a two-dimensional manifold. Calculus 3, you'd study surfaces. All your surfaces have two dimensions because you're talking about a two-dimensional surface. This continues to be true, like a curve in through space is one-dimensional because it has a one-dimensional tangent space, and so forth. So the story goes. What's the dimension then of SLN? Well, look, now we have, this is its tangent space at the identity. See, this is equal to the tangent space to the identity of SLN, right? Now let me not do it for arbitrary n. Let's keep it simple. Let's make it two-dimensional because I'm tired. So n equals to 2. So you've got v equals to what you got. You got a, b, c, d, with the trace of v equal to 0. So what is v equal to? A, b, c. Got to put a minus a here, right? Does that make sense? So in other words, SL2R is the span of, well, 1, 0, 0, minus 1, 0, 1, 1, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0. What did I claim the dimension of SLN was? It was what? N squared
minus 1.
N squared minus 1?
No.
Yeah, n squared minus 1. You got it right. So n squared, and what's our dimension here? 3, right? 4, 2 squared minus 1. Let's check my claim about the bracket. So the commutator bracket, guys, is AB is equal to AB minus BA. My unsubstantiated claim at the moment is that the commutator bracket of elements of the Lie algebra is again in the Lie algebra. Can we check that out for these? Like what happens when you calculate? So you guys help me out here. What do you get when you do 1, 0, 0, minus 1 times 0, 1, 0, 0? What's that give us? And what happens when we multiply in the other way?
Thinking what's in my head, imagining what you would say.
So I got 0, 0, and I've got 1, 0. This one, I get 0, 0, and I get minus 1, 0. So when I calculate the commutator of 1, 0, 0, minus 1 with 0, 1, 0, 0, I get twice 0, 1, 0, 0. I think twice. Did I do right? AB is that, and then minus BA. So that's an illustration, but you can calculate, you can go ahead, try it out. If you calculate the commutator bracket of any two of these, you'll get back one of them again, or twice of it. It's in the span of them anyway. So you see that SL2R, it's closed under the commutator bracket. All right. We could do more, but I think I'll just leave it at that for the explicit calculation here. Is that okay? Now, what about ON? What about the orthogonal? So example, what am I on, example 3? So let's calculate what is the Lie algebra of ON R. What's that going to look like? So if, I'm going to use B instead of V just because B is nicer. If B is an element of the Lie algebra of ON R, then e to the TB is an element of ON R, right? Now, we can't always just have everything magically fall into our lap either because it's a property of the matrix exponential like in example 1, or because there's this fantastic trace identity like in example 2. Sometimes we have to work for our food, you know, and this is like one of those. So what does it mean for this to be in there? Well, it means that e to the TB, right, transpose times e to the TB is equal to the identity, right? This is the condition. A transpose A equals to the identity. This is what defines it being an orthogonal matrix. So, yeah, you want to solve for B, right? But that, you know, to quote my community college professor, that dog will not hunt. So what you want to do here is differentiate. So if we differentiate that, that will bring B down to our level. And then we'll differentiate. So when you differentiate, you get e to the TB transpose times B transpose e to the TB plus e to the TB transpose times e to the TB times B. Now, you can write the B before or after the exponential, whatever. What's the derivative of the identity matrix? That's easier, right? 0. Now, last time I chided you guys for putting t equal to 0. But no longer. See, because now t equals to 0 is your friend. Put t equal to 0, what do you get? What is e to the 0? Yes, it's the identity matrix, right? It's 1 in this context. So all of this just shrivels away to B transpose. All of this becomes B. And so the condition, apparently, is simply that B transpose is equal to minus B. In other words, yeah?
So that means that, like, you have, what, symmetric matrix, or like, you have the symmetric matrix around the diagonal, or just negatives?
Yeah, this is an anti-symmetric matrix. So that means the diagonals are 0 and the off diagonals above determine the off diagonals below, right? So like, but the special orthogonal SONR, excuse me, not special, just the orthogonal ONR is B in Rn by n, such that, well, B transpose is minus B. This is the tangent space to the identity of big ON R. So, you know, notice this, by the way. Big SON R is equal to ON R intersected with SLN R. So like, if you think about this, what is little SON going to be? It's going to be the same as ON, and the reason for this is, so, I mean, my question is, if you think about, what I'm trying to get at here is if we have e to the TB is already sorry, brain stopped working all of a sudden. Dumb. I don't think what I wrote is wrong. I just don't have a way of explaining it. Just a second here. So what I'm trying to get at is these matrices are 0 on the diagonal.
Yes.
So these already trace B equal to 0. So that tells me that ONR, right, is a subset of SLN. And anyway, the larger point here, guys, is that this is equal to SON, little SONR. And the reason for that, and I should use the script S here. That's what's typically done. And the reason for that is just that the determinant 1 condition doesn't, that makes it have to be traceless, but these are already traceless. There's something like larger geometric that's going on here is ON, it's got 2 pieces, right? So like ON, here's a picture, here's what's going on. All right, it's disconnected. ON's got 2 pieces. See, on the one hand, you've got SON. On the other piece, you've got minus SON, all right? Altogether, it's ON. The identity is here, right? And so the tangent space to the identity of SON is equal to the tangent space to the identity of ON, because they're the same tangent space. And as such, it's the same Lie algebra. So like, this is our first example, perhaps, of we have two distinct Lie groups, right? ON and SON, these are different Lie groups. ON has plus or minus 1 determinant matrices, SON does not. But they have the same Lie algebra. Okay, so like there can be different Lie groups that have the same Lie algebra. Let's see if I can show you guys anything else here today. Any questions?
Many, but none that come to mind right now.
Many.
Yes.
Let's see here. Yeah, I think what I'm going to do going forward, as we go through the Lie algebra, as we study Lie algebras and we look at different examples, I'm going to try to just talk about the corresponding Lie groups as we come to it, just to make it more interesting. So, if that's okay with you guys, so it won't take much of our time really to do that. And let's see here. I was going to tell you. Let's see here. So let's see here. So Sophus Lie is rightly recognized as the creator of the theory of continuous groups. A major stride in the development of their structure, their theory, which was to have profound influence on their subsequent development of mathematics, was made by Wilhelm Killing, who in 1888 published the first paper in a series entitled Die Zusammensetzung, I'm saying that wrong, der Steigen and Licken Transformation Gruppen, that kind of comes through, which is translated, the composition of continuous finite transformation groups. The work of Killing, later refined and generalized by Élie Cartan, led to the classification of semi-simple Lie algebras. Cartan's theory of symmetric spaces and Hermann Weyl's description of representations of compact semi-simple Lie groups using highest weights. So it says, Weyl brought to the early period of development the theory of Lie groups to fruition. Not only did he classify the irreducible representations of semi-simple Lie groups and connect the theory of groups with quantum mechanics, but he also put Lie's theory on a firmer foundation, a firmer footing by clearly enunciating the distinction between Lie's infinitesimal groups, which we now call Lie algebras, and Lie groups proper. And he began investigations of the topology of Lie groups. The theory of Lie groups was systematically reworked in modern mathematical language in a monograph by Claude Chevalier. And so he says, Lie groups are smooth differentiable manifolds, and such can be studied using differential calculus. In contrast, the case of more general topological groups, one of the key ideas of the Lie groups is to replace the global object of the group with its local or linearized version, which Lie himself called its infinitesimal group, and it has since become known the Lie algebra. So like, to start with, as often is the case, mathematicians had all of this, like the group and the algebra were not separate. They were like put together, and you know, you can approximate the group by its algebra. You can do things like that, right? So like that's a lot of like where this all started. And the confusion between the Lie group and the Lie algebra persists in physics literature if you read some of it from not too long ago. But anyway, I mean, for example, another place in physics literature, the tangent space and the manifold are confused. In a lot of like Misner, Thorne, and Wheeler's book called Gravitation, there's sort of an implicit confusion between the manifold and the tangent space. And, these are things that we kind of have to work past. And, so much of physics is approximations, so it's not as bad as it sounds from like a mathematician's perspective is like you're mixing data types, right? But that's not quite how physicists do things. So, and this, like so many other parts of math, is born from physics in the 19th century. And it's the other major direction of group theory. Like Galois theory was the other, large impetus to studying permutation groups, because Galois theory understood that by studying how roots to the polynomial equation rotate into each other, if you study that group that's formed by the roots of a polynomial equation, you can study the structure of the group, and if that group is solvable, it turns out, then if the Lie group of a polynomial is solvable, that means that you can set the equation in terms of a radical extension of the coefficients of the field over which the polynomial is built. So so-called radical extension, which is sort of the corresponding idea to solving a quadratic equation in terms of the quadratic formula. So for a polynomial with a solvable Lie group, there exists sort of a quadratic formula. In contrast, if the Galois group for a polynomial is simple, it turns out that means it's not solvable, and it correspondingly is the fact that you cannot write down an equation for all the solutions of that polynomial equal to 0 in terms of a radical extension. Like the zeros to the polynomial don't exist in a radical extension. You need something else. This is Galois theory. This was discovered by Galois in 1830 or so. And then that's a lot of what built up interest in group theory to start with, was that. The other side is transformation groups, Klein and Lie. This is the other, driving, interest that drives us to be interested in group theory. Really different questions both came to the concept of a group. And then groups just naturally arise in other things, like anytime. They're just everywhere if you start looking for them. But there's also something called differential Galois theory. You can study, like, when is it possible to solve a differential equation using functions of a particular type that corresponds in a similar way to extending the function field in a particular way. And this gives rise to theorems like you've heard before. You can't write the integral of the Gaussian function e to the x squared in terms of elementary functions. Well, where does that kind of claim come from? What's the mathematics that establishes these kinds of claims? Well, that's sort of the same corner of math as the differential Galois theory. They're the ones that have the tools to answer those kinds of questions. But it's sophisticated, it's difficult. I can't explain it quickly. I can't explain it well. I have some handouts if you're interested that my brother wrote when he taught an honors DiffEQ course or something, where he went into this with some students. I think he had like a pod of students that he met with weekly to do things. So, well, if you end up going to app, then you can talk to Bill about that if you're interested. But let's see here. So, look, what would happen with that GJ space? You can start to see through these calculations, right? What's the Lie algebra for we had that GJ space, right? So what was the defining condition? The defining condition was what? It was A transpose, J, A equal to J, right? So if I just get straight to the, straight to the, you're okay. Oh. If I just get straight to the, the critical calculation, we have what? If we put A equal to e to the TB, right? You get e to the TB transpose J e to the TB equal to J. Differentiate this, right? Differentiate this, we get e to the TB transpose times B transpose J e to the TB plus e to the tb transpose j e to the tb times b equal to 0. And then you know what we're going to do.
Yeah, I mean, it's the same trick that we did before.
Yeah.
BT plus B, or yeah.
Exactly. Put
BTJ plus JBT.
right, exactly. B transpose J
0.
plus JB equal to 0. And so there you go. That becomes the defining condition for the Lie algebra. Let's call it frac J, G frac. So that would be like Lie of this guy. And that, of course, that is going to cover a multitude of examples. See, because that, that will cover what the Lie algebra look like for example, the Lorentz group. We put J equal to eta. Okay, and so many other things. All right, when J is equal to I, this becomes the antisymmetric condition. Yeah. The other thing that complicates this, as you try to understand its connection with physics, is in physics, they like to work with Hermitian operators, and so they end up putting an I in the exponential formula, which changes like symmetric things to like anti-Hermitian things or something like that. So there's some wrinkles in terms of the formalism making direct contact with quantum mechanics. You have to like filter your thinking through their physicsy ways. But all right, so let me end today with the definition of a Lie algebra. So what is a Lie algebra? It doesn't have to be a set of matrices, right? But for us, for today, it's been a set of matrices. But what a Lie algebra is this. So A is, well, let's say L. L is Lie algebra if L is vector space over some field F, right? Such that bracket from L cross L goes back to L again is bilinear and try to get things off on, started on the right foot here. So, oh, he uses capital L, so I've already used the wrong letter. My bad. There, I'll fix it. It's not too late. Sorry. And this bracket has the following properties. It's bilinear, all right? You denote it as this. The pair xy maps to bracket xy, all right? And you have that x with x is equal to 0 for all x in L. And that, now watch this one here, x with yz plus, yeah, I gotta go. All right, yeah, quiet. I'm done. I'm almost done. This plus y with zx plus z with xy equal to 0. And this is, of course, for all x, y, z, and L. All right? That is a Lie algebra. A Lie algebra is a vector space paired with a Lie bracket. So this is called a Lie bracket. Now, so the first thing I should dispel is like the Lie bracket does not have to be a commutator. A commutator is an example, but it's not the only one. But you can, through brute force, verify that the commutator bracket